Audiobook Academy Biography presents Carl Friedrich Gauss. Johann Friedrich Karl Gauss, aka Carl Friedrich Gauss, was a German mathematician who made significant contributions to number theory, geometry, probability theory, geodesy, planetary astronomy, the theory of functions, and potential theory, including electromagnetism. He was born on April 30, 1777, in Brunswick, Germany, and died on February 23, 1855, in Göttingen, Hanover. Poor parents raised Gauss as their sole child. He was one of the few math prodigies who was able to complete complex calculations in his mind throughout the majority of his life. Awed by this and his gift for languages, his instructors and mother referred him to the Duke of Brunswick in 1791, who offered him financial aid for his studies locally and then for mathematics at the University of Göttingen from 1795 to 1798. It wasn't until Gauss' pioneering work in mathematics established him as the year's most renowned mathematician that he became an aloof and distant figure to the public. In 1792, Gauss made the groundbreaking discovery that a regular 17-sided polygon could be formed using only a ruler and compass. What's important isn't so much the answer as the proof, which relied on a thorough examination of polynomial equation factorization and opened the door to later developments in Galois theory. There are as many roots, solutions, to a polynomial equation with real or complex coefficients as its degree, which he proved in his doctoral thesis from 1797. The highest power of the variable. The assessment of past attempts was outstanding, even though Gauss' proof did not fully convince. Later, on the 50th anniversary of the initial proof, Gauss provided 3 further proofs, demonstrating the value that he placed on this work. However, it wasn't until 2 significant papers in 1801 that Gauss was acknowledged as a truly extraordinary genius. His most important work was the publishing of Disquisitiones Arithmeticae, the first comprehensive textbook on algebraic number theory. Modular arithmetic, quadratic polynomials in 2 variables and integers, and factorization theory are all covered in this book. For most of the 19th century, Gauss's continued interest in number theory inspired a great deal of research, particularly in German universities, on the subject. The Asteroid Series was rediscovered in his second article. Before enough observations could be obtained to accurately determine its orbit, it retreated behind the Sun before its next appearance could be predicted by Italian astronomer Giuseppe Piazzi in 1800. Gauss was the only astronomer to find it again, despite the efforts of many others. The method of least squares he developed to deal with observational errors was the key to his success. Gauss then worked as an astronomer for many years and released a big book on the computation of orbits, which was much easier for him numerically than for other people to do at the time. A loyal follower of the Brunswick and Hanover families, Gauss believed that his work had a socially beneficial impact on his community. It was for these and other reasons that Gauss accepted the job of surveying the province of Hanover, spending much of his time conducting field work. It was a long and tough endeavor, lasting from 1818 to 1832, but it yielded a slew of innovations as a result. Some were made more precise by Gauss' creation of the Heliotrope, an apparatus for reflecting solar rays in an intense beam that can be detected from a distance of many miles. As an example, the discovery of the idea of surface curvature was one of his many contributions. Gauss discovered that if a surface is bent without stretching, it retains an intrinsic measure of curvature. For instance, because the intrinsic curvature of a circular cylinder and a flat sheet of paper are identical, precise replicas of cylinder figures can be created on paper, as, for example, in printing. Because a sphere has a different curvature than a plane, it is impossible to create an accurate flat map of the Earth. Number theory, the mathematical science of map creation and many other disciplines were all covered by Gauss in his writings. With his newfound interest in terrestrial magnetism throughout the 1830s, he joined the world's first ever survey of Earth's magnetic field in 1839. To measure it, he invented the magnetometer. Although he made the first electric telegraph with his Göttingen colleague, Wilhelm Weber, a certain parochialism hindered him from pursuing the innovation more vigorously. A significant branch of mathematics in the study of electromagnetic and gravity was born out of his work on what is now known as potential theory. In addition to his work in mathematics, Gauss also penned numerous articles on the subject of cartography and the science of map projections. A prize from the Danish Academy of Sciences was given to him in 1823 for his work on angle-preserving maps. This study got very near to proposing that complex functions of a complex variable are often angle-preserving, but Gauss stopped short of making that essential insight explicit, leaving it to Bernhard Riemann, who had a profound appreciation for Gauss's work. In addition, Gauss had a number of private revelations to friends about the nature of complex functions and their integrals that were never published. In truth, Gauss kept many of his findings from the public. He began to have doubts about the a priori reality of Euclidean geometry while a student at Göttingen and suspected that it might be empirically true. An alternate space geometric description must exist for this to be true. Gauss opted not to give a detailed exposition of Euclidean geometry, instead focusing on attacking various a priori defenses of the discipline. The evidence suggests that he was eventually persuaded that there is a logical alternative to Euclidean geometry that he could not ignore. The new non-Euclidean geometry described by Hungarian János Bolyai and Russian Nikolai Lobachevsky was published about 1830, nevertheless, when Gauss was asked to explain his own ideas, he could not. As a result of his work on intrinsic curvature, Gauss theories can be put together into a stunning whole, although he never did this. This failure has been attributed by some to his intrinsic conservatism, others to his incessant inventiveness that always drew him to the next new concept, and yet others to his inability to establish a central principle that would rule geometry once Euclidean geometry was no longer unique. There is value in each of these hypotheses, but none is complete. Elliptic functions were another area where Gauss kept his thoughts to himself. When he wrote about an interesting infinite series in 1812, it was published, but he never published an account of the differential equation that it solves. Many well-known and new functions can be defined using the hypergeometric series, which he demonstrated. But by then, he had figured out how to use the differential equation to build a highly general theory of elliptic functions and to free the theory from its roots in the theory of elliptic integrals. After discovering that elliptic functions are naturally complex-valued, Gauss in the 1790s determined that complex integrals couldn't be used for this purpose. This was a big advance. In 1830, the Norwegian Niels Abel and the German Carl Jacobi published some of this idea, and Gauss remarked to a friend that Abel had come one-third of the way in his hypothesis. Although this was correct, it is a sad reflection on Gauss's character that he refused to make it public. In a variety of other respects, as well, Gauss fell short of his own expectations. He did not want to expand the University of Göttingen or bring in additional students because it was already small. Contemporaries described his writing style as thin gruel because it is clear but lacking in inspiration and can be tedious to read. He was a great aid to the mathematicians Richard Dedekind and Riemann who came through Göttingen at the conclusion of his life. People who were bold enough to write to him were frequently, but not always, supported by him in public. However, Lobachevsky was once assaulted by fellow Russians for his non-Euclidean geometric theories. For the Göttingen Academy of Sciences, Gauss learned Russian so he could keep up with the debate and suggest Lobachevsky. However, in a letter to Bolyai, Gauss claimed to have already found all that Bolyai had recently written about in his latest work. His influence lasted well into the 20th century thanks to the revelation of so many new ideas in the unpublished works of Gauss after his death in 1855. There had not been a breakthrough in the acceptance of non-Euclidean geometry prior to the publication of Riemann's general ideas about geometry, Beltrami's explicit and rigorous account, and the private notes and correspondence of Gauss at the same time as the original work by Bolyai and Lobachevsky. Thank you for listening in Audiobook Academy. Don't forget to subscribe and smash that like button for more content like this. See you in next video.